In the previous video, I went over how Hello World works on my computer here. So check that out if you want to hear about my C compiler for this processor and what it takes to write to the screen. There is more to it than you might think. Here I made some use of all of that and wrote a hex editor to become a bit more independent of other computers. This is the source code, pretty short thanks to the compiler. It would have been a lot longer in assembly. The compiler generated assembly looks like this. Anyways, enough of that, let's just run it. This is what it looks like. As you can see, it just tells you the value at every address in memory. And you can scroll through them to edit them. You can already see there's something changing when I press buttons. At address 1 is actually where the buttons that are currently held down are stored. So you can see every button has its own little bit in there. Here we have some other global variables. For example, this value relates to the x position of where lines are drawn. So if I increment that, then the line below it shifts by 1 pixel. And if I add 16, then it shifts by 16 pixels. Down here you can see the data starting to look a bit more random. Those are the OLED characters, so the very characters that you can see on screen right now are stored there. Well, specifically not down here. The first character we draw is the star, which is stored at address hex 83. So I can just go down there. And well, that's 85, but it's still part of the star. So I can just edit this, and as you can see, the star now changes. Oh, if I go up here, I can add a few pixels too. And now we've successfully corrupted the star. And the funny thing about this is it stays like this because all of this is non-volatile memory. So this is where global variables are being stored. One other really interesting region of RAM we can look at is the stack. As you can see, the stack pointer starts at hex C000. So scrolling up there would take a while, so I'm just going to patch the program to start there. And there we go. That's the hex editor starting at C000. The stack. You can already see there's a lot of stuff going on here. The very first address is actually the return address, though this program never terminates, so we don't really care about that. Then when I move the cursor, you can already see this value here change. That's the currently selected line. Similarly, right below it, we have the currently selected column. So if I want to, I can now also change these by just editing the memory value. That also works. And this value right here is C000, so that is the same as the address in the upper left. So for anyone who complained that there isn't a go to address functionality, all you have to do is edit memory at C001. And now, for example, we are at D001. You can't really go to very many places like this, but I guess it's better than nothing. Those are the interesting things to look at in regular memory, but in this architecture that's separate from where the program is stored. This is regular memory, and this is program memory. For obvious reasons, I also really want to edit that. So I made a little version 2 of the hex editor, which I'm just going to upload. And it looks like this. As you can see, it gives us a little prompt where we can set the address we want to start editing at. And also we can decide if we want to edit RAM or program memory. So let's just look at program memory. This starts at 4000, which is the same area where the program is being stored. So this is actually the hex editor right here. It's assembly. Most of these instructions, if I edit them, are obviously just going to break the program. But there's a few of them that aren't quite so critical, and here we have one of them. If we look at the disassembly, we can see this is the instruction that's conveniently at 1024 relative to 4000, and it pushes FFFF. By doing so, it passes the color white, which is FFFF, as a parameter to one of the methods that draws characters or numbers. So you can already see the FFFF here. I can just go ahead and change that to push a different value, and now the star is pink instead of white. Change something else too. Yeah, and well, this way we can change the color of the star. And just like before, this is a permanent change, because everything is non-volatile. The star is now pink. We've successfully customized this program. But the real reason I made this hex editor was obviously to write entirely new programs independently of any other computer. So that's what we're going to do now. To do that, I'm just going to go to address 6000, which is far enough away from anything else to not cause any problems. And then we can edit PRAM, still with our nice pink cursor. As you can see right now, it's all ones. That's just a factory condition for these chips. But I'm going to write a little program that counts using R0 and R1, so a 32-bit counter. And the very first thing we want to do is always add 1 to R1. That's our low word. So these first two characters are the low byte of the literal. So in this case we want this to be 1 because we want to add 1. Then in this case the next characters are the high byte of the literal. So we want this to be 0 because we want to just add 1, not any more than that. There we go. Next we have the opcode, which we want to be 1, because that's add. Okay, that's the address we don't really care about because we don't have any memory access in this instruction. Then we have the source, which is going to be E, which is a full-size literal. And we have the destination, which is going to be R1, which is 2. Makes sense, right? That's the first instruction written. Let's move on to the next. This is a little bit more complex, because this is a conditional instruction. We only want to add 1 to R0 if R1 just overflowed. Well, the first part is certainly the same. The literal is still 1, because if we add, then we do want to add 1. Then in this case, the next two characters are not going to be the high byte of the literal. They are going to be the condition and the destination. So the condition in this case is going to be carry, which is D. Then the destination is R0, which is 1. The opcode is still add. The memory address we still don't care about, but it can't be F, because then this will be interpreted as a full-size literal. So I'm just going to set it to 1. That shouldn't cause any problems. Okay. Then we have the source B, which we want to be a half-size literal, which is F, so that's already correct. And source A, which we want to be R0, so 1. Okay, there we go. So let's move on to the next instruction. This is just a jump back to the beginning. So in this case, it's going to be a subtract from instruction pointer 3, because for technical reasons, when we are at this instruction, then the instruction pointer already points here. So if we subtract 1, 2, 3, then we are back at the beginning. So we just set the literal to 3. In this case, we don't have a condition or 3 operands, so we can just use a full-size literal again, which is a little easier. Or maybe I do actually need to press the button more often, I'm not sure. Okay, the opcode is going to be 2, which is subtract. There we go. Then the memory address we still don't care about. Then we have the source, which is going to be a full-size literal again. And then we have the destination, which is going to be A10. That is the instruction pointer. There we go. So that's really all there is to it. That's the program. So how do we get there? I could just reset the system and then use the dip switches to set the instruction pointer to 6000. But there's actually a nicer way to do this. To do that, I have to reset again, and we have to go to our old friend the stack again at C000 and edit RAM there. I mentioned earlier that the very first thing here, C000, is the return address. That's where the computer goes to after the current program, so the hex editor has terminated. And in this case, 4003 is just an infinite loop where it pretty much waits until it's reset or halted. But we can obviously edit this to whatever we like. And I'm just going to set it to 6000, which is where the program we just wrote is. And that's really all there is to it. Now all I have to do is exit the hex editor. For that I have a little escape sequence. I press right and then left. And there you go. Now you can see we have the 32-bit counter on R0 and R1. You can also see the reason why I made it 32 bits. At 2 MHz it just counts so fast that you really can't see anything going on in R1. Okay, so that is the first program that is written entirely independently of any other computers. The only external help we had was some power, but everything was done using the hex editor, so that's pretty cool. Now, obviously this process was still very, very tedious to do, and I hope to make it a little bit easier in the videos to come. But this is it for now. Thank you so much for watching, and see you next time.